We continue our study of distributions and distributions of supports of distributions and distributions with compact support. Okay, before that, one erratum. In the previous lecture, I was trying to prove the following, namely, if omega tilde is union I in I, omega I, then and if t restricted to omega I equal to 0, this implies that t restricted to omega tilde is also 0. This is true for all I in I. This is what I was trying to prove, and in the process I used a partition of unity, psi I C locally finite C infinity partition of unity. So in the subsequent things, I made some confusion in the notation, namely sometimes I use phi I, sometimes I use psi I. So what we meant is that support of psi I is contained in omega I for all I, and then the family support of psi I is locally finite, and then 0 less than or equal to psi I less than or equal to 1, and finally sigma psi I is identical equal to 1. So there were some were written in terms of phi, sometimes in terms of psi, and so on. And if you took phi in d of omega tilde, then you have phi equals sigma over I phi psi I, and phi tilde is equal to sigma over I phi psi I tilde. Okay, so there was some of these were written in terms of phi I instead of psi I, so please correct it. I sorry for the confusion. Okay, so now we continue with distributions with compact support. Okay, so if t, so omega contained in Rn open set, and t equals t is a distribution on omega, and support of t is equal to k compact. Then we saw that if phi naught is identically 1 in a neighborhood of k, phi naught in d omega, this implies that t equals phi naught of t. Okay, so this we saw, and we saw that distributions with compact support are precisely E prime of omega, so namely the dual of the space of C infinity functions. Okay, so these are the what we have already seen. So now we have the following proposition: omega contained in Rn open set, and t in d prime omega, t belonging to E prime of omega. That means t is a distribution which has compact support. So this is the notation: distributions with compact support are denoted by E prime of omega. Okay, then t has finite order. Recall the order of a distribution. If you have a distribution phi t, then mod t phi is less than or equal to ck times norm phi n of k for all phi such that support of phi is contained in a fixed compact set k, and if n of k were independent of this compact set, then we say that it is that integer n which works for all compact sets is called the order of the distribution. So, and then we say T is a distribution of finite order. So here we want to show that every distribution with compact support has in fact in fact a distribution of finite order. Okay. So let K equal support of T compact, and you take phi naught in d omega and phi naught identically equal to 1 in a neighborhood of K. We usually say phi naught equal to 1 in K, but you can also take a slightly larger compact set than K, and there also you can construct phi naught to be equal to 1. So there's always you can choose phi naught such that phi naught is in a 1 in the neighborhood of K. Okay, so then of course T equals phi naught of T. Okay, so let K1 be the support of phi naught. Now let phi belong to d of omega. Okay, then phi naught has support contained in K1. Okay, and so this implies that mod T phi, which is equal to mod of T phi naught phi, by since we have the T equals phi naught of T, this is less than or equal to C of K1 times norm phi naught phi in NK1. Okay, but by Leibniz formula, we have that norm of phi naught phi in K1 is less than or equal to some constant times norm of phi in NK1. Because what is Leibniz formula? It just says that this derivative, all the derivatives of phi naught phi, linear combinations of derivatives of phi naught and derivatives of phi. Now derivatives of phi naught are all uniformly bounded, so they can all be absorbed in the constant here, and therefore you have just derivatives of phi which have to be estimated, and so you get this. Therefore you have that mod T phi is less than or equal to CK1 times C. So this is, I can put all this in some other constant times norm phi NK1 for all phi in d omega. So this implies that T has order NK1. Okay, so this is every distribution has finite order. Now we saw that the Dirac distribution delta and d alpha delta all have support singleton 0. Okay, and so true for all finite linear combinations of these distributions. Now we show that the converse is also true. Namely, if you have a distribution which is supported only at the origin, then it has to be a linear combination of Dirac and its derivatives. Okay, so before we prove that, we prove a very beautiful, you might have seen it when you did the functional analysis course. So here is a lemma. Okay, so E vector space and lambda 1 etc. up to lambda n linear functionals. So there is no question of continuity here because we are just taking a vector space. So assume intersection k equals 1 to n of the kernel of lambda k is contained in kernel of lambda. Then there exist scalars alpha 1 to alpha n such that lambda is sigma k equals 1 to n alpha I alpha k lambda k. Okay, so this is a very nice, many nice theorems can be proved from this, and let us show this. Okay. So proof. So we will of course know, without loss of generality, we will assume base field is R. We are through doing this. So okay. So now you consider the map phi from E to Rn plus 1. So phi of x is equal to lambda x, lambda 1x, lambda nx. So this, so range of phi is a linear subspace of Rn plus 1. And by hypothesis 1 0 0 does not belong to range of phi. Why? Because if for some x you have 1 0 0 equal to this, then lambda 1x to lambda nx is equal to 0. So x belongs to the intersection of the kernels, and therefore lambda of x must also be 0, but we are given that lambda of x equal to 1. So 1 is not there. Therefore by Hahn-Banach, there exists a linear functional on Rn plus 1. But what is a linear functional on Rn plus 1? It's nothing but n plus 1 scalars, such that its action on 1 0 0, namely beta naught, is not equal to 0, and sigma action on the range beta naught lambda x plus sigma k equals 1 to n beta k lambda kx equal to 0 for all x in E. So this is nothing but a statement of Hahn-Banach theorem. So now because beta naught is equal to 0, so result follows with alpha I, k equals minus beta k by beta naught. Okay, so that proves this lemma. So we will now use this lemma to prove the following proposition. So theorem: T in D prime of Rn such that support of T equal to 0. Then there exists integer, an integer k greater or equal to 0, and scalars C alpha for all multi-indices alpha such that mod alpha is less than or equal to k, such that T is equal to C naught sigma mod alpha less than or equal to k of C alpha D alpha delta, where delta is the Dirac distribution. So we saw that linear combinations of the Dirac and its derivatives has support 0. Now we are proving the converse, namely if you have support equal to 0, singleton 0, then it must be only a linear combination of the Dirac and its derivatives. So proof. Okay, so we let phi belong to D of Rn such that d alpha phi equal to at 0 equal to 0 for all mod alpha less than or equal to k. That means that phi belongs to kernel of d alpha delta for all mod alpha less than or equal to k. Okay, so we will show that t phi equal to 0. So then by lemma t equals sigma mod alpha less than or equal to k of d alpha delta. Alpha equal to 0 corresponds to just delta, that is this. Okay. So that will prove the theorem. So enough to show that t of phi equal to 0. So let epsilon be greater than 0. Okay. Then for all x in a sufficiently small neighborhood of the origin, we have d alpha phi x is less than or equal to epsilon for all mod alpha equal to k. Because you have the d alpha dk, d alpha phi 0 is 0 for all mod alpha equal to k in particular. Therefore, in a small neighborhood, all of them will be less than epsilon. So let us take, okay. Okay, so before, so the first, so what is k? So before we start the proof, we say since singleton 0 equals support t is compact, t has finite order k. Okay, so then we will show the following things. Okay, so this is, so k is the order of the distribution. Okay, so by the mean value theorem, since all derivatives of order k are less than or equal to all derivatives up to order k are equal to 0 at the origin, and d alpha phi x for mod alpha equal to k is less than or equal to epsilon, it follows that mod phi x is less than or equal to c epsilon times mod x power k. This is just the mean value theorem, which says you can estimate the function in terms of the derivative times the monomial concerned. Okay, so c greater or equal to 0 depends on n and k. Now apply the same reasoning to d alpha x now, d alpha phi of x, where 0 is less than mod alpha less than k. Okay, so we have actually done it for 0 now, so we apply it. So mod d alpha phi of x in a small neighborhood will be less than or equal to c epsilon times. Now from alpha you have to go to the kth order derivative, so therefore you will have mod x to the k minus mod alpha. Is just I'm writing d alpha phi x as an expansion in the neighborhood of the origin. All derivatives up to k minus alpha of this function, namely all derivatives up to order k of the original function, are all 0, and therefore by the mean value theorem once again you have this. Therefore, combining these two, we have that so combining, so call this 1, call this 2, combining 1 and 2, we have that mod d alpha phi of x is less than or equal to some C epsilon mod x to the mod k minus mod alpha for all 0 less than or equal to alpha, strictly mod alpha less than k, less than or equal to. Okay. Okay. So now let phi 1 belong to D of Rn such that support of phi 1 is contained in the ball center origin and radius 1, and phi 1 identically equal to 1 in a small neighborhood of the origin. Okay, again this is the cutoff functions which we have. Then for eta positive, define phi eta of x equals phi 1 of x over eta. Then support of phi eta will be contained in the ball center origin and radius eta, and you have phi eta will still be equal to 1 in a small neighborhood of the origin. Now you take d of alpha phi eta of x, this is equal to sigma, I am writing the Leibniz formula. This is C alpha beta. These are the combinatorial coefficients alpha by alpha minus alpha factorial by alpha minus beta factorial times beta factorial, and into d of alpha minus beta phi 1 phi eta of x times d beta of phi x, and phi eta is x by eta, and therefore this will give you sigma beta less than or equal to alpha C alpha beta d alpha minus beta phi 1 of x by eta into d beta phi of x, and then by eta will come 1 by eta to this power d alpha minus beta, that will come, so that will give you eta to the power of mod beta minus mod alpha. So if mod x is less than eta, then we have norm of phi eta k is less than or equal to C epsilon times norm phi 1 k, because of this relationship which we already have. Okay, so this is d alpha phi x is less than that. If mod x is less than eta, it is less than c times C epsilon times k minus mod alpha, and therefore you have this. Okay, but phi eta is 1 in a neighborhood of origin, and what is and support of t is nothing but singleton origin. So this implies t equals phi eta of t, and therefore we have t of mod t of phi equals mod of t of phi eta phi, which is less than or equal to c times norm phi eta phi k, because that's the order of the distribution, and that is less than or equal to C epsilon times norm phi 1 k. Now epsilon is arbitrary, phi 1 is a fixed function, and this implies that t of phi equal to 0. Therefore d alpha phi equal to 0 for all mod alpha less than or equal to k implies t of phi equal to 0. So by the lemma we have that t is in fact equal to sigma mod alpha less than or equal to k d alpha delta c alpha times d alpha delta.